Today we're going to be talking about basically what is the point, right? What are the objectives that we care about when we are optimizing for the operation or the design of a distributed energy resource or a collection of DERs. So this will tie together, I hope, some of the kind of more conceptual material that we learned about convex optimization and optimization in general over the last few weeks, and then make it a little more concrete kind of in the context of the DERs that we've been learning about. So we'll start by talking about just a little bit, just a tiny flavor of sort of economics and policy of the electricity sector. Just a few slides. You can take a whole class on this. It's super interesting historical and economic and political material, and we will obviously just scratch the surface in like 5 or 10 minutes. But hopefully I'll give you at least enough context to make the rest of this lecture make maybe a little bit more sense. Then we'll talk about some reminders, basically just results from the last couple of lectures about optimization that will be relevant today. Then we'll talk about linear objectives. There are a lot of these, things like minimizing the cost of energy or pollution that comes from using energy. Then we'll talk about nonlinear objectives, and there are a lot of those as well. And then I'll wrap up if we have time. I have a lot of slides today, so I don't know if we'll get there, but if we don't do it today, we'll do it next lecture. But I'll wrap up by talking about a reference tracking example. So this is basically you have some power signal, a target that you want to follow with maybe the power consumption of a battery or the power output of communities, something like that. And so we'll talk about that a little bit. Okay, so the traditional model, and this is still the model in maybe 40% of the United States, is that electricity comes from what are called vertically integrated utilities. So here we have the physical setup. This is generation, basically power plants, a flow of electricity from there into the transmission network. So this is high voltage power lines. And we want high voltage for long distance transmission because higher voltage allows more power to be transmitted at lower current. And resistive heating losses, Joule heating losses on power lines go like current squared. So the higher voltage, lower current means lower losses, squared lower losses, basically. The transmission system feeds power into the distribution system, which is typically at a medium voltage. So this is on the order of 100 kilovolts. Distribution will typically be on the order of kind of 10 kilovolts. And then that will go to loads. These are buildings, factories, and so forth. And typically they operate at low voltage, so on the order of 100 volts. So in this model, basically users, people who pay for electricity and the services that we get from it, usually are in buildings, but again, manufacturing facilities and things like that. And we are responsible basically for the loads. And then one business, which is a regulated monopoly. Regulated means that there is a government agency that basically oversees, gives approval to the company for what they can do. So you have one entity basically that manages the generation, transmission, and distribution assets. And then there's a state regulator. This could be called a public utility commission, a public service commission, something like this. And it could be elected in some states, or it's appointed by either the governor or the state legislature in other states. And it's typically on the order of like 3 to 6 individuals, many of whom worked or will work again for the utility, but also maybe people who are politically connected or academics, lawyers, and so forth. So there's basically an information flow between the regulator and the utility. And that might look like, for example, the utility says, oh, the cost of fuel for my power plants is going up. And so I need to charge ratepayers more money to recoup those costs. And they would go to the regulator and ask for a rate hike. And then the regulator would say yes or no, or something in between. So historically, actually, these monopoly utilities were not regulated. So actually, they weren't monopolies originally. So if we go back to kind of the very early days of the electricity system in the United States, when Edison and others, Westinghouse and Tesla were building out power plants, and there were fights over DC versus AC, as Aaron mentioned in our DC house tour. In the very early days, there were sort of many players, and people were building little power stations and little power lines to provide lighting and so forth, kind of in little pockets of cities and neighborhoods and so on. And then Edison's successor, a guy named Samuel Insull, basically went on a project where he tried to buy up and consolidate pretty much all the utilities in the US, or as many as he could. And so he did that in most of the big urban areas. And then you had true monopolies that were unregulated, that were doing things that monopolies were doing in that era of the call them the robber barons, right? This is kind of the era when railroad prices were going crazy and all that. You probably remember this from like a social studies class in high school, right? Anyway, so people got mad about that, and there was a lot of pushback and protest, and there was a push toward what's called municipalization of electric utilities, where cities would say, hey, we could just buy out your poles and wires and power plants and do this ourselves, not nonprofit. And that basically, became a credible threat. And then there was negotiation, and the kind of compromise that came out of that tension is the current model that we have here, where basically the state guaranteed monopoly status, so protection from competition for these companies, and in exchange they surrendered some of their autonomy, basically saying that these proxies for people, at least nominally elected in kind of a democratic process, would get to oversee what the utility can and can't do. Okay, so that's the basic model, and this, again, about 40% of electricity sales in the US are covered by this model. There's another model which came about mostly in the late 1990s through the 2000s, and this is what's called competitive wholesale electricity markets. So the physical system looks the same. We still have all the same assets, but the economic and political arrangement is quite different. So the users still are responsible for the loads, and they still pay money, often to still a regulated monopoly utility, but sometimes there is competition kind of at the retail level as well. But then the companies that own the transmission and the generation are in general separate from the utility. Some utilities do own both transmission and distribution, but usually they're not allowed to own all three. So the generation assets basically were divested. And then there is another entity here called an independent system operator, ISO, or pronounced ISO. And this is basically a nonprofit organization that runs the electricity markets. So basically, all the money that ratepayers pay to utilities essentially goes into the markets that are run by ISOs, and then get hopefully fairly paid out to the people who own transmission lines and to the people who own power plants. And so this entity, the independent system operator, both does a lot of engineering and a lot of economics, and they basically figure out which power plants should be running at any particular time in order to maintain reliability in the system at timescales, going from fractions of a second all the way up to looking years ahead. So they want to ensure if there's a lot of load growth from new heat pumps or electric vehicles or whatever, that there's enough power lines and transformers and generation to keep up with that demand. So they have a very challenging task, and there's a lot of really interesting stuff that goes into it. And I won't say much about it other than it's cool, and if you're interested, you should learn more. Okay. So that's kind of the two systems there. And the stuff here, so this is a map basically of where there are ISOs and where there aren't in the United States. So I think there are 7. There's the California ISO. ERCOT is in Texas. So this is the Electric Reliability Consortium of Texas, I think. We in Indiana are under MISO, the Mid-Continent ISO. And then there's the biggest one in the US is called the PJM interconnection. That stands for Pennsylvania, Jersey, and Maryland. And that's where that ISO originated, but it has grown to cover a significant portion of the Eastern Seaboard, and actually stretches all the way west to the Chicago area as well. And then there's New York ISO and ISO New England. And all the things that aren't covered in ISOs are in this kind of vertically integrated utility model. And so the Southeast is basically all in that model. I forgot one, the Southwest Power Pool. This is kind of a more or less an ISO as well. But the West is also kind of in the vertically integrated model today too. Okay, so I just want to make basically a clarification between wholesale and resale. So in the world of business or whatever, wholesale just means basically bulk stuff. So if I am a farmer and I have a lot of land and I grow a lot of crop, I don't know, cabbages, I might sell them, in bulk at the wholesale level to a company that is a retailer. That might be a grocery store chain. And then they would, take my produce and send it out to all their grocery stores and so forth. And so the price that I sell is going to be, that I sell cabbages at wholesale is going to be lower than the retail price, because that retailer has to, maintain shops and a distribution network and things like that. And so it's analogous basically how the electricity system works at the wholesale and the retail level. So this is a graph of time on the x-axis, and then the price of electricity on the y-axis in units of cents per kilowatt hour. And the top here, the black curve, is basically the retail price. And this is in New England. So if we look back at the map, this is kind of the upper Northeast here. that area. So the retail price is up here, and it's made out of two components. The dark blue here is the energy component, and then the light blue here is called the delivery component. So roughly speaking, this is for using the energy, this is for the energy that actually flows over the power lines and through the transformers. And then this is a cost that's associated with basically recouping the capital investment and all those poles and wires. And the yellow curve here is the wholesale electricity price. So one trend to note is that on average, it's maybe about 4 cents per kilowatt hour. It has a lot of variability to it, whereas the retail electricity price is maybe on the order of 16 cents a kilowatt hour. So there's kind of, roughly a factor of 3 to 5, something like that, difference between wholesale and retail. And then, yeah, there's a lot more volatility kind of at the wholesale level. And you can almost look at this as kind of a filtered version of the yellow signal. So it does kind of have spikes when the yellow has spikes, but they're sort of attenuated, if that makes sense. And that's because I guess you could say that the companies that do the retailing of electricity absorb some of the risk associated with the volatility of that wholesale price signal. Okay, and then there are different customer classes in the world of retail. So, if we had the wholesale price at maybe 3 or 4 cents a kilowatt hour, somewhere down here, the retail price is not only quite a bit higher, but it's quite a bit different for different customer classes. So the people who pay the highest price for electricity are people like you and me, who buy electricity for use in houses. And then essentially the bigger you get, the less you pay for electricity, for a unit of energy. So commercial, this is, office buildings and hospitals and things like that. And then industrial, this would be manufacturing facilities and so forth. So if you look at the difference between the industrial price, maybe 12 cents a kilowatt hour, and the residential price in New England, and maybe 21 cents a kilowatt hour, there's about a 50% increase over the industrial price. So, for whatever reason. So sometimes there's good reason for that. So sometimes an industrial facility might plug in kind of further upstream in that physical chain of delivery of electricity. So they might plug in at a higher voltage point in the network, and so there's just less infrastructure needed to get power to them. But also there may be bulk discounts and other reasons that they have lower prices. Okay, so that's just a crash course in a little bit of kind of the organization of the electricity sector. Let's talk just a little bit about some reminders about optimization that'll be relevant today. So you may remember that a function of n variables, a scalar valued function of n variables, is linear if it can be written as the inner product of some vector a with the vector x. And then it's affine if it has that same form, but then there's an offset as well. So y equals mx plus b, the thing that we all called linear in calculus class, we now call affine because reasons. Okay, so linear functions are all affine, but the converse, of course, is not true. And affine functions are both convex and concave. And in fact, that's a one-to-one equivalency. So anything that is both concave and convex is linear. Sorry, is affine. Okay, and then we also talked about curvature a little bit a lecture or two ago. And so in the special case of an affine function, we have we talked about curvature and monotonicity. So in the special case of an affine function, we have that it's non-decreasing, basically if the coefficient ai corresponding to a variable xi is non-negative. And then if that ai is negative, we get that the function is non-increasing in xi. And we also talked about how minimizing an affine function, ax plus b, if you're minimizing that over the variable x, that's equivalent to just minimizing ax. Basically, a constant you can't affect, so no choice of x can change the value of that b that you get, so you can essentially take it out of the cost function, and it doesn't affect the solutions. We also talked about composition rules for both curvature, convexity, concavity, linearity, and also for monotonicity. So we had that a convex function of an affine function is convex, and that's true regardless of the monotonicity properties or lack thereof. A convex non-decreasing function of a general convex function is convex. And then if you have a convex non-increasing function of a concave function, that ends up being convex as well. And then we have similar rules for concave functions. These are generally not as useful for us, but sometimes they come in handy. So concave of affine is concave, concave non-decreasing of concave is again concave, and then concave non-increasing of a convex function is concave. So these all kind of look, similar to the convex versions. And then for monotonicity, if we have a non-decreasing function of a non-decreasing function, that is again non-decreasing. And then if you have a composition of two non-increasing functions, that composition is non-decreasing. And then we have some additional rules. Basically, if you have a composition of a non-increasing and a non-decreasing, that ends up being non-increasing, and the bottom one here holds as well. Okay, so last time, I think it was Levi asked a question, why is it that convex functions of convex functions are not necessarily convex? We also have this monotonicity condition that the function is non-decreasing. So here is a very simple counterexample that occurred to me at about 5 minutes after I went to the lecture the other day. So just for your curiosity here. So suppose we have a function g and h, and we're interested in the composition of g and h, so g of h of x. So if g of y is negative y, and h of x is x squared. Okay, so h is convex, x squared is a convex function, and g is affine. It's just a linear function here with a slope of -1. And affine functions are convex, so now g is a convex function. But we don't have the monotonicity property that we want, right? We want convex non-decreasing in order to get a convex composition. But we have convex non-increasing here. So the composition then, g of h of x, is just negative x squared. And that is not bowl-shaped, right? It's concave. So this is one simple counterexample that shows why you need to be a little bit careful with just convex of convex. You need to look for the curvature, the monotonicity properties as well. Does that make sense? Okay, and then I want to just talk a little bit about our DER models and try to make somewhat more concrete how we are sort of mapping the DER models that we spent a month learning about into these kind of optimization problems that we've been talking about more recently. So at the very end, we did kind of a summary lecture on DER modeling, and we showed that essentially all of the DERs we talked about, other than solar photovoltaics and some deferrable loads, can be modeled basically with something that looks quite like a battery model. So we have a linear, first order linear discrete time dynamics equation here. And then we have a bunch of linear constraints on both the state x and the action u. And then we have, in general, a nonlinear function g that maps the state and the action into the electric power, which is usually what we care about when we talk about the economics and other objectives in DER optimization. So the state here has the interpretation as a stored energy. It could be the chemical energy in a battery. It could be the thermal energy in the thermal mass of a building or in the air inside of a room. It could be the thermal energy stored in water, either through phase changing, freezing and thawing, or through just sensible heating. And it has various other interpretations depending on the DER. And then the action, the kind of knob that we can twiddle, typically we can look at as being the power that's used to either charge or discharge kind of our energy storage element. So this could be the power that's going into a battery for an electric vehicle. It could be the power that's going into a heat pump, something like that. And we talked sometimes about how this action U, rather than being the absolute power, it can be kind of a perturbation of the power. So we can have some baseline, for example, what this building might be using for air conditioning on this unseasonably warm March day. And then you might say, okay, well, if we change all the temperature set points, basically we'll wiggle around that baseline in some way. And so the energy stored is kind of this virtual energy, I guess, that's defined relative to that baseline. And then there's typically, or in general, a disturbance, and this could have to do with, for example, people drawing water out of a water heater, or it could have to do with people putting mileage on an electric car. So here A and B are discrete time dynamics parameters, and they have particular definitions for each of the DERs we talked about. And then the sort of limits here on X and U are capacity limits on the energy and on the power. Okay, and this function g, it has a different form depending on the DERs that we're talking about. And the most general form of it is that it is either affine in X and U, or that it is a convex function. So it has nice properties, it turns out. And those properties end up being useful for the kind of optimization stuff that we're about to do. So a fairly general, not completely general, but general enough for our purposes right now, optimization problem involving DERs then could be formulated in a way like this. So basically our decision variables would be the states at every time. over some discrete time span that here I'm indexing from 0, which would be, right now the initial time, all the way up to a final time k. You could think of this as a day or a month ahead. And then U, this is the action, so basically the charging power, and then P is the power consumption the electric power consumption that we use. And we want to minimize some function of P naught all the way through Pk minus 1, which we can look at as a big vector, essentially, of power consumption at every time step. And we'll talk about many different forms that function could take, and that's kind of the point of today's lecture. And then we have a bunch of constraints. Typically, we have a constraint around the initial state of the system. So how much energy is initially stored in a battery or a water heater. And then at every time step, we have constraints related to the dynamics, right? So this is basically the physics of the problem. Also the capacity of the devices. And then, how much basically control authority we have, how far we can twiddle the knobs, the action. And then we also have this equality constraint that comes out of our basically power mapping. And then we have a bunch of input data. So the initial state x naught, these parameters A and B that show up in the dynamics. And then at every time step, we have a disturbance, we have state limits, and we have action limits. And then we have also these functions G, which can vary depending on the time. But these functions have to all be defined in order for this problem to be kind of well-defined and solvable. So this is pretty close to the form that we would need to put this into CVX. I won't talk about exactly how to do that and show sample CVX code today, but next lecture I will. And the nice thing to note here is that basically this function G that gives the electric power is either affine or convex. And so that means that when we talk about the actual objective function, whether it's energy or pollution or peak demand or something else, that we want to pay attention basically to the kind of the composition rules that arise when we do a composition of our objective function with this function G, which gives the electric power as a function of kind of the basic decision variables, the state and the action. So if G is affine, then anything that's convex in P is good. That's convex in X and U as well. But if G is itself convex, then we need to be a little bit careful, right? Because convex of convex is not necessarily convex. Right, so there we need to also pay attention to monotonicity of the objective function. Does this make sense? Ish. Okay. All right, so let's give some examples then, but hopefully make this stuff a little bit more concrete. So I think the simplest objective that you can think of when optimizing a DER or a fleet of DERs is just to minimize the energy. And so there, that's very simple. It's just the time duration of time step basically times the power that's used over the time step. You might also care about the cost of energy. And basically energy used at 4 p.m. might not have the same value as energy used at 4 in the morning. So you might have a time varying electricity price that basically differentiates between energy usage at different times. So regardless of the formulation here, whether you're talking energy or energy cost, we end up having a linear function of the power, which is nice. And then it's non-decreasing as long as this coefficient that's multiplying P, the price pi E here, as long as that is non-negative. Now, there are weird examples where the price of electricity can go negative. So in Texas, for example, there is a ton of wind. And in the middle of the night, when there's not a lot of electricity being used in oil refineries and buildings and houses and stuff like that, there's very high supply from wind, and there can be very low demand. And so you actually have excess power on the grid. And so the grid operator will pay people basically to use all that free, abundant wind. So that can happen. It's kind of a pathological case, but it actually may happen more and more as we get more and more of these kind of random renewables on electricity grids. Okay, so what do electricity prices look like? There's a bunch of different options. Actually, Leo, who is our visiting scholar from Germany, and I were just discussing this yesterday, that the topic of kind of designing rate plans in order to promote behavior that is in some way beneficial for the electric grid is like a really deep and interesting research topic in its own right. But here are some of the things that are used in practice currently. So here in Indiana, we have, at least I have, just a flat electricity price. So I pay about 15 cents per kilowatt hour of electricity, regardless of the time of day or the season or anything like that. There is also what's called time of use pricing, and this is kind of a typical residential time of use rate plan, where typically in the evening, people start coming home from work and turning on lights and cooking and TVs and things like that. And so demand for electricity goes up. Also, production from solar power is going down at that time. And so you get tighter basically matching between supply and demand, and that can lead to higher prices. So to reflect that at the retail level, utilities will sometimes charge a higher price basically during those peak periods. For a commercial building, usually this would be moved kind of to the middle of the day, the working hours when demand is usually higher. And typically these time of use rate schemes are designed such that if you had constant load, just a flat, using 1 kilowatt constantly, that you would pay the same amount whether you were on the flat pricing scheme or on the time of use pricing scheme. So basically that means if you integrate these things, the area under both curves is equal. So you can see that we have a little bit of a lower cost kind of in the off-peak periods, a lower price rather, in the off-peak periods to make up for the fact that we have a higher price during the peak period. Yes.
Quick questions, maybe a little unrelated, but do you think that seems like fair, or do you think this seems like a little scummy? Do you think this is like incentivizing people to have more uniform load, or are they like, oh, we know you're going to use more money in the or use more energy in the evening, so like?
Yeah. So the question is this fair, basically, or are utilities doing this basically to try to make more money off of people? I don't know. I mean, like most things in the world, the answer is probably a bit of both. I think that there is an equity or a fairness consideration here, which is that some people know more about energy. Some people are more aware of the prices that they pay. Some people know the things they can do in their homes to reduce energy usage at certain times, and other people don't or don't have the time to think about it or whatever. And so there tend to be kind of affluence type effects differentiating those two groups. And so you might say, it's unfair to poor people who have less time to think about this stuff, right? And I think that's certainly true. And that's, I think, for that reason, almost always time of use rate plans in the residential customer class are opt-in. So by default, you're on a flat rate, but you can choose to be on a time of use rate if you want. That's not universally the case, but that's typically the case. I do think that a kind of an equalizer would be having more automation, basically to coordinate the devices that are used in houses, right? Because then you kind of don't have to think too much about it. If everybody had some kind of cool, clever software that could, pre-cool their house before people get home, and then drift through this a little bit and so forth. That it would kind of, as long as everybody had it, everybody would sort of have an equal ability to sort of shift load around. But no, it's a good question. Thanks. Any other questions? And please feel free, of course, as always, to raise your hand. Okay, so that's what a time of use price looks like, at least in residential. There's also something called a critical peak price plan, and these are much less common. So time of use is much less common than a flat rate. And then critical peak pricing is, again, much less common than time of use pricing. So I don't want you guys to think that this is like a normal thing, but it is something that people think about. So the idea here is that you get kind of on normal days when everything is sort of cool and stable on the grid, and there's not a risk that you're going to have a power outage somewhere due to a lack of supply or whatever. On normal days, you basically get a discount for signing up for this plan. So we have maybe the same kind of structure that we would have for a time of use plan, but the whole thing is just dropped down by a cent or two per kilowatt hour. But then in exchange for that, you basically are subject to a very high price during these periods where reliability or supply is very constrained on the grid. And so the idea is, a day ahead of some really bad event, which usually is just driven by really, really hot weather and air conditioning demand going through the roof. In advance, maybe a day ahead of that critical peak event, you would get a notification from the utility that says, hey, from 4 to 6 p.m., so right, from 2 to 6 p.m. tomorrow, we're going to do a critical peak pricing event, and your price of electricity will go way up. So I pulled this from a rate plan in California that just says, look, add 50 cents per kilowatt hour to the price during this window. So again, like if you imagine you forget about this or you don't know how to shift your load around to respond to this, you're going to end up paying a bunch of money for electricity during that period. But the goal is that you figure out something else, right? So you decide, oh, okay, I'll take my kid to the movie theater during that period and just turn off everything in my house, right? Something like that. Okay, and then this is what the real time or the wholesale price of electricity looks like. This is today's electricity prices in MISO where we are. I just downloaded these and threw them into a plot. One thing I want you to note is that the y-axis here is very different from the previous plots. So in all the other plots, the upper y limit was 80 cents per kilowatt hour, and here it's 3.5 cents per kilowatt hour. So there's just a very big difference there. But you can see that overnight, the price is a little bit low. During the day, as people start waking up and using power, demand gets higher and the price gets a little bit higher. And then the price peak is kind of in this afternoon or evening window, again, when people are coming home and using a bunch of power. So there are pricing plans that you can get at the retail level in some places that have a price that's basically tied to this wholesale price, which is different from one day to the next. It'll vary depending on the weather and other things. So most people don't have a rate plan like that, but some do. Yes.
I have a bit more of a conceptual question. So if we, as we mentioned, like we multiply this price scheme by our power consumption throughout the day, that's still a convex optimization problem. And is that just because we are taking discrete time steps and assuming it's constant in between in this situation? Or like, I guess just conceptually the mathematics like don't make sense in my head. But
Yeah. Okay. So the question is basically if we take this wiggly thing and we multiply it by our power, how is that convex, right?
Yeah.
So we think convex has to be sort of bowl-shaped or at worst sort of linear. And here we have, dips and peaks and valleys and stuff like that. So so the answer there of how does this end up still being a convex optimization problem is that the convexity really has to be we think of it as convexity of a function of our decision variables, the stuff that we're choosing. So that would be something like the power that we're putting into a battery or the heat that we're putting into a thermal storage system, something like that. So this is a function of time, right? So it's really, if we go back to the optimization formulation here, it's really this function here, the function of the power demand. We want sort of convexity in P, if that makes sense. So we don't really care about if it's convex in T in time.
okay.
Yeah. I guess another way to look at that mathematically is that here, for anything, regardless of the price, at any given time, we're just taking some number and multiplying it by P. So we always have a linear function of P, basically. Okay.
Yeah.
Okay, cool. Thanks. Yeah, good question. Okay, so that's energy and the cost of energy. We can also talk about pollution. So there are various pollutants that we might care about, carbon dioxide, maybe being emitted by power plants, methane, either maybe being leaked from natural gas infrastructure. Also oxides of nitrogen and sulfur can be air pollution that can have pretty detrimental effects on folks' respiratory health. So you might care about reducing that pollution, either the volume of it, or you might assign essentially a price to it. And so here mu is the intensity, the pollutant intensity of electricity at a given time. So for example, at 2 p.m., you might have a lot of coal power plants running, which typically emit a lot of air pollution, local air pollution. And so mu might be high at that time. And then at some other time, maybe there's a lot of wind and solar on the grid, and so mu might be quite a bit lower. And so you can imagine shifting load around basically in order to kind of do a buy low, sell high thing, but with respect to how clean or dirty electricity is. And then here, the price pi g would just be a way to convert essentially something like a mass pollution into a dollar value. So you could think about the health of impacts and what that is worth to society and so forth. And then you could kind of imagine having a mixture of, I care about the cost that I'm paying for energy, but I also care about how much pollution is being emitted sort of on my behalf, things like that. Okay, so both of these are linear and non-decreasing in the electric power P. And I think they're always non-decreasing because I think the prices and the pollutant intensity are always non-negative. I can't think of a situation in which you'd have a negative pollutant intensity. So that'd be like you're running a power plant that is somehow absorbing CO2 from the atmosphere and producing electricity, which I don't think thermodynamics would like that very much. And then the price here, I think you'd have to be sort of sociopathic to say, I want to emit more pollution, right? So I think that one is always non-negative as well. We can also talk about demand flexibility. So now we're getting into more esoteric things, right? Like I think energy cost is it's like ubiquitous. I think everybody cares about that. It's the money that we pay for utility bills. Pollution, some people care about, and demand flexibility is like a weird thing that DER nerds care about. Okay, so anyway, flexibility, at least defined here, kind of in the DER context, I would say is the capacity or the capability to adjust your electric power kind of on demand, on call. So either through an automated signal that's sent to you by a grid operator, or maybe through a price signal, something like that, an economic signal. And grid operators will pay DERs, typically not individual DERs, but aggregations, collections of a large number of DERs, which in the industry they call virtual power plants or VPPs. So they will pay VPP operators to either plan flexibility and or to actually use the flexibility to, for example, respond to some emergency on the grid. So typically decision-making in the grid is done kind of in two stages. One is a day ahead, a plan is made, and then in real time, they kind of make adjustments to that plan to reflect the realities kind of on the ground. So to fit into that framework, a DER aggregator might make a plan, sort of a baseline power trajectory, but then they might also basically have some flexibility. They can say, yeah, at 2 p.m. tomorrow, I think I'll be using 100 kilowatts, but I could go as high as 120 or as low as 80, something like that. And then in real time, the grid operator might say, ooh, I desperately need you to use more power because there's a bunch of free solar on the grid in your area. We're getting over voltage issues in the grid, something like that. Okay, so what does that look like in terms of an objective? So typically, the stuff, the DERs that we're using will have capacity constraints, both upper and lower power constraints. So this is kind of, maybe the baseline, the plan that we're at might be, up here at about 80% of the capacity. And we could ramp upwards an amount P max minus P. We could also ramp downwards an amount P minus P minimum, basically. And so we can define the upward flexibility and the downward flexibility accordingly. And typically, grid operators will assign some value to the ability to kind of ramp up and or to ramp down. And then they will pay DER aggregators in order to basically provide that flexibility. So whether you're going up or going down, you're affine in P, which is kind of nice. But the monotonicity properties are different. So upward flexibility, you can imagine, is basically a thing that's saying, go lower. It's like pushing power down, encouraging power to be pushed down, which is similar to just having a price of electricity. So to have more upward flexibility, you want to move P to the left here. So that ends up being non-decreasing, which is, I think I actually mixed this up here. Anyway, so we get different monotonicity properties depending on whether you're doing upward or downward flexibility. And then as long as we have a non-negative price, if the value of flexibility is positive, then the monotonicity properties basically are preserved here. Okay, so that was kind of individual linear objectives. But what if we have a couple of linear objectives? We care both about energy cost and also about pollution, or about flexibility, something like that. Well, it turns out that combinations of linear objectives end up still being linear, just with a new price. So as one example, suppose that we care both about the energy cost here, and we also care about the pollution cost over here. So we could combine them basically by defining a new price, pi, which would just be the price of electricity plus the price of the pollution, maybe a carbon price, times the, say, carbon intensity of electricity. And you could do this as well if you had demand flexibility and stuff in there too. We can also talk about aggregate objectives. So if you don't just have one DER, one battery in one house, say, but maybe you are Tesla and you have thousands of batteries all over the San Francisco Bay Area, and you want to do something collectively with that whole population of batteries. In that case, as long as your objective is linear in P, it ends up being linear in all the individual DER powers as well. So the aggregate power here is just defined as the sum of all the individual powers, and then possibly with some other uncontrolled load kind of mixed up in there as well. Demand from houses or something like that, or supply from renewables. So the aggregate power is affine and non-decreasing in each of the PI. It's just the sum of a bunch of individual powers. And so any of the curvature or the monotonicity attributes that we've talked about applying to the function P extend directly, apply in the same way to each of the individual PI powers. Yes?
I don't know if this is like a clear answer, but how does the time to optimize change if you increase it from a scalar optimization to, let's say, a vector of 2? So if you have, instead of solving for one battery, you have 2 batteries, is it just double, or is it like?
So how does the computation time to solve the optimization problem, how does that scale with the number, say, of DERs? So it depends on the structure of the optimization problem. So if it's a linear program, it'll typically scale kind of about linearly. Actually, I had the scaling with the dimensions of the problem in, I don't remember them off the top of my head, but in slides a couple of lectures ago. So we talked about the complexity of least squares, of linear programming, and then maybe a couple of others.
Yeah.
But so it's polynomial. It's typically goes like n cubed or something like that, where n is the number of devices. So the problems can get big quickly. So if you have 1,000 batteries, you could end up trying to solve a really huge optimization problem. And it might take, if you're trying to make a decision every 5 minutes, it might take longer than 5 minutes to solve, and then you'd be kind of out of luck. And so there are optimization techniques you can use to basically decompose one big problem into kind of a set of coupled smaller problems that you could solve in parallel on parallel processors or GPUs or something like that. And there are algorithms for that. It's called distributed optimization. Or you can design your control system differently. So rather than having decision-making be central, you could have each of the kind of distributed batteries or whatever making their own decisions, and then design that algorithm in such a way that kind of the overall behavior of the whole collection is good. So that's another, it's a distributed control problem, basically. Okay. And then, okay, so that was kind of aggregating over space, if you like, many different DERs in different locations. We could also aggregate over time through what are called cumulative objectives. So typically we don't just care about what happens at 2 p.m. tomorrow. We might care about what happens over the whole day. So we'd add that up basically over time. And sometimes when we do that process of accumulating costs or benefits over time, we use what's called a discount factor. The idea here is that most people would rather have $1 in their hand right now than $1 a year from now. But there's usually some amount that you would take. Yeah, I'll wait a year to take that payout, right? Maybe it's $1.10 or $1.50 or something like that. And so that's called the time value of money, basically. And so it basically means that money right now is a little bit more valuable than money later. So to reflect that, we take some number, gamma, usually it's less than 1, but maybe it's 0.999 or something like that. And we take gamma and raise it to k, where k is the index, the time index. So if we're looking right now, k is equal to 0, and this gamma to the 0 is going to be 1 for whatever value of gamma. But if we're looking ahead, say a day or a month or a year, gamma to the k might end up being significantly smaller. Okay, so then if we take the cumulative discounted cost, well, that's just adding up this term gamma to the k delta t times our price at time k times the power we use at time k. So we add that up for the initial time, k equal to 0, all the way up through the end time, t is equal to k minus 1. And so that ends up just being an inner product between a vector a and p, which means that this is a linear function of the electric power. And so P here is just the stacked vector of all the powers at each time step. And then A is just basically a vector of all the coefficients that are multiplying P here. So it's delta T times gamma to the K times pi of K for each K. Okay, so already we've gotten a fair amount of complexity, right? We've gotten energy efficiency, we've got energy cost, we've got pollution efficiency and the cost of pollution. We've got demand flexibility from kind of a planning framework. And we can do some financial discounting, and we can look ahead over kind of arbitrary horizons, time horizons. And we can look around in space at kind of arbitrarily large if we want optimization, or sorry, aggregations of DERs. So just with linear objectives, we already get quite a large kind of range of stuff, cool stuff that we could potentially do. But if we allow nonlinear objectives, then it kind of grows from there. So let's talk about a few of those. And one of them shows up in the homework. I think it's the very last part of the last homework problem that we're doing this week. So here we're dealing with solar power on a building. and we have what's called a reduced net metering plan. The idea here is that in a one-to-one net metering plan, the price that you buy electricity at from the utility, the 15 cents a kilowatt hour or whatever that we pay, is the same price that we would sell excess solar power to the utility that we export from our panels. So we would have just a linear thing here. But in a reduced net metering scheme, you would get paid less for the power that you export than you would get for the power that you import. So one way to think about this is, if the utility can buy electricity wholesale on the bulk market for 3 cents a kilowatt hour, why should they be forced to pay you 15 cents a kilowatt hour for the solar on your roof? There are counter arguments to that argument, but that's just like one rationale for doing these things. Okay, so this is a convex and non-decreasing function, which is quite nice. That's what we were looking for kind of convexity of the overall DER optimization problem. So here P would be interpreted as the net power. So that's the demand minus the supply, say, from a solar panel. And then the energy cost associated with this reduced net metering thing is not a linear function, but it has this convexity and monotonicity property that's quite nice. So we can write that just as the max of the blue line here, which is the buy price times P, and then the orange line here, which is the sell price times P. So you can see, you could imagine extending this orange line out to the right and extending the blue line down to the left here. And you just always pick the bigger of those two lines, basically. Yes?
So like with this model, are we assuming that net power demand is just like everything is being normalized by having to buy however much electricity you need outright? So I think that was the part that I was confused on. Almost like if demand is higher than supply, then I understand that you have to buy from the utility. But then if your supply is greater than the demand, you still need to buy. You still need to buy like electricity, and then you just sell the extra stuff. Or am I understanding that?
Yes. No, I think you are understanding it correctly. Let me try to paraphrase the question for folks online. Okay, so in this model, suppose you have a building that has solar panels on the roof. And so you have demand from like the air conditioning and stuff, and then you have supply from the solar photovoltaics. So you were saying you understand in the situation where you have more demand in the building than you have supply on the roof, basically. And in that case, maybe you're consuming 10 kilowatts and you're producing 8 kilowatts. And so your overall demand, your net, is 2 kilowatts. And then you still have to buy that from the utility, right? But in the other situation where you have, say it's the middle of the day on a spring day when you don't need any air conditioning, right? So demand is quite low, say 2 kilowatts, but we're still producing, say, 8 kilowatts from the solar. Then our net demand is going to be 2 minus 8, so negative 6. So we'll be down here somewhere. So the idea there is that you always prioritize using your own solar power locally when you can. So it's first you use, say, 2 kW from the solar in the house to run the fridge and the router and whatever. And then the leftovers you take out to the utility and you sell it back. And then they buy it at a lower price than they would sell you electricity. Does that make sense? Okay, cool. Okay, so that is energy cost when we have these kind of asymmetric buying and selling prices. There's also what's called symmetric demand flexibility. So we talked about upward demand flexibility, the ability to kind of consume more power. We also talked about the ability to consume less power and how both of those could potentially be valuable. Some grid operators, some ISOs will pay for only for symmetric flexibility. So they don't want to think about whether you're moving up or down. They just want to know your ability to move, basically. And so here you would take the smaller of your upward flexibility and your downward flexibility. And in this case, the upward flexibility is smaller. So then that ends up being our symmetric flexibility. So PJM, the biggest ISO in the US, for example, at least last time I checked, they paid for this kind of symmetric flexibility service, not an upward and a downward. Whereas the California ISO pays for upward and downward ramping separately. Anyway, so this is a concave function because the minimum function is concave. And then in here, we have affine functions of P. So concave of affine is concave. But that's okay because this is a thing that we want to maximize. It's a thing we want to basically do as much of as we can. So maximize concave is okay for convex optimization. Peak demand. So after energy costs, actually, this is maybe the most common type of charge that shows up on actual electricity bills. So the idea here is that we need to size infrastructure not to kind of an average use case, but to a sort of worst case scenario. So it's really the kind of highest power on the hottest afternoon of the year that really drives how big, how thick power lines need to be, how big transformers need to be, and how many power plants we need to build. So the idea is by penalizing the peak demand of people, in buildings and so forth, you hope that penalizing sort of the local peak demand is a pretty good proxy or stand-in for penalizing demand at sort of these times when the overall grid is most stressed. So here the blue, you can imagine, I'm just plotting versus time, this could be your electricity demand. And then rather than charging for the energy, which would be the integral, the area under the blue curve, we just charge for the peak, the highest point on the blue curve. And so pi d, the price will be non-negative in general. And so we have basically a non-negative scalar times the max function, which is convex and non-decreasing. So peak demand is cool. It fits nicely within our convex optimization framework. The price pi d is typically for, so you most often see actual demand charges on industrial or commercial electricity rate plans. They're not so common for residential rate plans. And again, I think this gets back kind of to the fairness issue that you brought up. But for these commercial and industrial plans, it varies depending on where you are in the country and stuff like that. But typically we're kind of in the range of $10 to $50 per kilowatt for the peak that happens over an entire month. Now you might not be able to optimize for DER, operation with a fleet of DERs. You might not be able to look ahead, at a 5-minute time step for an entire month. It might not even make sense to do that, right? You might have no idea what a price will be or what the weather will be doing a month from now. But typically we can get weather forecasts and price forecasts and stuff at least a day ahead. So you might want to penalize the peak a day ahead rather than a month ahead. And if you do that kind of every day, then that roughly is equivalent-ish to charging about $1 per kilowatt kind of over a 1-day horizon. So if you did that 30 times over a month, you would end up charging kind of about $30 per kilowatt, which is sort of the midpoint of this monthly peak range. Does that make sense? This might not be the best thing to do, it might or might not. It kind of depends. People also sometimes use what are called target demand limits. So this is in that context when I was talking about where maybe you get billed for the monthly peak demand, but you're optimizing kind of looking ahead over a 1-day horizon. You might say, I'm only going to penalize peaks if they exceed my target demand limit. And so, for the month of March, we might simply look back at March of last year and say, oh, for our, campus, the peak demand was 50 megawatts last March. And so we're going to basically say, let's aim for 45 megawatts. Maybe we can keep the peak below that. And we're only going to penalize peaks if they go above that. So the idea is if you have a mild day where you're only using 10 or 15 megawatts, who cares if it's 10 or 15, right? It's not going to be the sort of peak that sets this monthly charge that we get billed based on. So, so this target demand limit basically allows you to kind of stop caring so much about those daily kind of mild day peaks. Okay, so the idea then is we take the max between 0 and the max of P minus the target demand limit. So the idea here is this is our maybe 45 megawatts that we want to stay below. If the blue curve was shifted down here, then the max of P would be less than L. So it would be max P minus L would be negative. And then this whole thing here would just give 0 because 0 is larger than say -5, right? But if we are above so the peak of the blue curve is above the orange dashed line here, then maybe this is 5. And so we'd be taking the max of 0 and 5. That would be 5. And so we end up being paid essentially for the excess of the peak there. Does that make sense? Okay. So now we're getting into like weird and esoteric territory. We're getting to the point where like if you took a couple of these objectives that I'm talking about now and you put them into a paper and you did some careful simulations, that you could publish that. Right. So this is now weird enough that like it's at the frontier of research. Okay. And it's going to get, I think, a little weirder from here still. Okay, so anyway, the peak demand, this even with this sort of target demand limit in there, ends up being a convex and a non-decreasing function of P. So again, that's kind of exactly what we were looking for. So this is nice, clean, fits into our framework easily. There's also something called coincident peak demand. So if you look at skyscrapers in New York that might have, many millions of dollars of electricity bills for, a bunch of apartments and 50 stories and so forth, oftentimes they get paid what's called a coincident, or they have to pay what's called a coincident peak demand charge. And the idea here is that, again, kind of peak demand is all about penalizing the need to basically upgrade infrastructure. And that need is usually triggered by sort of a bulk, whole system level peak demand. So what's happening at my particular building might not really matter very much unless it happens to line up in a really bad way with what's happening kind of with the rest of the buildings in New York, right? Okay, so the idea then is we have some window where we have the system peak demand happening, and you take a maximum of the power curve here, but only over that window. So we ignore everything else and we just pick out sort of the crucial time period. And then we say, how much did you contribute over that time period? Okay, so that was your contribution to basically the requirement to build out all this new infrastructure. And so we're going to penalize you for that. Okay. Does that framework sort of make sense? Yes.
That shift.
And this may shift, yes. And so again, this gets back to the sort of fairness issue and the need for automation and stuff, because it's usually not clear very far in advance when these peak periods will actually happen. So you may know, maybe a day ahead, you may have forecasts of demand provided, basically the whole grid demand provided by the system operator. And the system operator always knows basically how much capacity they have, how much transmission and generation and so forth. So, that number is known. And then if the demand forecast for the next day is really close to that number, then you might start saying, okay, I think tomorrow we're going to have a peaking event. So you might say, I'm going to be really careful about what we do during these peak hours.
Does that affect people's decision-making, like at that instant, as soon as they find that out, they're like, oh, we have a peak, we should turn everything on now, because it's going to cost us a lot in a couple of hours or something?
Yeah, so the question is basically, does that affect people's kind of real-time decision-making? And the answer is, yeah, it can. Kind of the traditional way that buildings are operated in a place like New York, you would not be really aware of this at all. People would just kind of keep doing whatever they're doing. And at the end of the month, you would get a bill and be like, why is it so high? And then, you might hire a consultant who would go through and read, line by line, your electricity rate plan, like all the legalese, which is a huge pain in the butt to do. And then they would find, oh, you have what's called a coincident peak demand charge. And so because the grid, the overall New York ISO grid, peaked at 2 p.m. last Tuesday, and you happen to be, running your air conditioner full blast and blow drying your hair and whatever, you ended up paying an arm and a leg basically because of your peak demand at that time. So again, I think this really gets back to the need for automation, because you typically, even for a gigantic skyscraper in New York, like they do have energy management professionals who do know about this kind of stuff, but they're usually like also the people who have to go and fix things when they're broken and who have to deal with complaints coming from occupants and stuff like that. And they're usually overworked and underpaid, and they probably don't have time to actually do stuff like this, optimize stuff like this. So that is basically where the need for software comes in. And so I ran away. I'm getting so behind here, but that's okay. I can do some of this on next lecture. Just one quick story. So a couple of colleagues of mine and I ran a workshop last September that was basically on smart buildings and trying to understand the state of research and the state of startups and established companies basically on smart buildings. And so a founder of a company called Q Coefficient, which operates in New York City, came in and was kind of offering words of wisdom in a presentation that he was giving to this audience of researchers, basically. And the number one thing that he said was learn how to read an electricity bill. And the idea is it's a huge pain in the butt, but once you understand what the incentives are, then it's actually not so hard to make smart decisions, right? You say, oh, okay, 2 p.m. tomorrow, it's going to be the system-wide peak, so I'm going to pre-cool my building, starting at 10 a.m., and then I'm going to, raise all the temperature set points by a few degrees and kind of coast through that peak period. And in that way, you save maybe 100 grand by just doing kind of simple logic for a big building. So Anyway, so yeah, it's useful stuff, but kind of arcane to think about. Okay, so that coincident peak demand charge mathematically, basically it looks just like the regular demand charge that we talked about, but now we have this weighting matrix C in here, multiplying P. So C is a square matrix and it's diagonal, and it's made up of these components C0 through CK minus 1, where the index there basically corresponds to the time stamp. So if C is equal to 1, that means that you're in a peak time, and C is 0 otherwise. So basically all this thing does, this matrix does, is it just picks out the demand, the portions of this curve P that happen within this critical peak period. Does that make sense? Okay, so this thing also ends up being convex and non-decreasing, which is great for us. There's also something called load reduction, or sometimes people call it demand response. But the idea here is, again, we have some window where the grid is really stressed for whatever reason. And there are programs that basically will pay people to reduce their demand below some baseline. And usually that baseline is calculated by a utility or by a demand response program operator, something like that. It's not something that you decide for yourself. So anyway, they say, look, we think your baseline 2 p.m. tomorrow when the grid is stressed is going to be 100 kilowatts, for your fleet of heat pumps. And so if you can reduce below that 100 kilowatts, we will pay you for that. And that price that they pay you at is usually quite high. So in California, it's $2 per kilowatt hour, whereas the wholesale price in California is usually about 2 cents per kilowatt hour. So it's a factor of 100 higher. And one wrinkle here is that they basically don't penalize you if you go above your baseline. So they reward you for going below, but they don't penalize you for going above. And so if we want to maximize the revenue, the payments that you would get from providing these kind of load reduction services, you would maximize the time step times your price, times the max, either of 0 or your baseline minus your actual power consumption. So here, if we're below the baseline, this thing will be positive. If we're above the baseline, it will be negative, and then we'll end up paying 0. Yes, question.
Your baseline.
How do they choose your baseline?
What's decided? So this is, I'm guessing, like this is for like a large building, California.
Yep.
What is their baseline? How do they quantify?
Yeah, so so the question basically is how do you quantify this baseline or estimate this baseline? Who does it, and what is it essentially? So if you're a big building, an office building in California, say, so it depends, and usually it's done by whoever's running the demand response program. Sometimes that's a utility, sometimes it's a third party. And the methods range from very simple to quite sophisticated. And the typical one is very simple. And it would just be basically like, okay, tomorrow at 2 p.m. is a Wednesday, and it's during this month. And so we'll look at the last 5 Wednesdays at that hour, and we'll average that, and that becomes your baseline. They also sometimes adjust for weather. So if it's hotter, your baseline might go up. And then there are super sophisticated methods that are used as well. So there's a company called Recurve that works in California, and they basically do the baseline of services for California demand response programs. And so they not only take into account, things like the time of day, whether it's a weekday or weekend, what the weather is like outside, but they also, and also your historical usage. So those all enter as basically features in a predictive model. But they also look at what other buildings are doing nearby. So you can imagine if you have a bunch of office buildings all run by different companies or whatever, if you know the load from one building, it's probably a pretty good predictor of what's happening in a nearby building, basically. So they throw all that stuff into a model, and they use linear regression essentially to make predictions.
That makes sense, because I could see something where it's like your baseline, if you keep going below your baseline, that becomes your baseline.
Right.
But if you don't get penalized to go above your baseline, there could be this loophole where for 1 month, you go below your baseline, next month, you increase your baseline. I don't know, I was just thinking of, like, depending on how you quantify the baseline, there can be.
Yeah, so the comment, I guess, is that you can kind of play games. You could imagine playing games with the baseline in order to kind of hack the rules here. And that's absolutely right. And actually, there was a pretty extreme example of that. It's almost a decade ago now. I forget what the stadium was, but it was like a big baseball stadium, basically. That they knew there was, an afternoon demand response program, that usually the calls for these demand response windows were typically, 2 to 6 p.m., something like that, when it's light outside, right? And so what they would do is they turned on all the lights on non-demand response days. They turned on all of their lights, basically. So they figured, okay, that's going to use more power on normal days. But the price differential between kind of my normal electricity price and how much I get paid for load reduction during these demand response windows is so high that it'll be worth it. So they artificially inflated their baseline. And then during demand response windows, they just turn off all the lights.
100 times.
And they save, 100x or whatever it is. Yeah, exactly. Right. So so that's one example. Another example is Bitcoin mining. So in Texas, there are Bitcoin mining operations. So Bitcoin mining, cryptocurrency, basically involves doing lots and lots and lots of calculations to essentially, to decrypt currency to enable transactions, essentially. So Bitcoin mining is like just having a big warehouse full of computers that are just running those calculations constantly. So they use tons of power to run all those computers. And then, so there are Bitcoin mining operations in Texas that actually make more money from providing services like this, basically from saying they can turn off all their servers on demand from the grid operators. So they make more money from doing that than they do from the actual crypto mining. So it's like totally backwards and bizarre. So
So just so I hear that, right, just by turning off the system, that they make more money from the operator. That's fair.
than they do, right? So like you can imagine, I don't know if this is true or not, but you can imagine just having like a bunch of heating elements in a lake or something,
Yeah.
and just like running them all the time, just using power and just running them, right? And then this is like the most extreme example, doing nothing useful for anybody, just burning off electricity that could be doing something useful. And then when the grid gets stressed, the grid operator calls you and says, could you please stop doing this? And then you do. And like, so if the price differentials are big enough, right? If during these emergencies, the prices get high enough, then that could be an economically viable, even profitable thing to do. So there are issues. I'm just trying to say you're absolutely right. There's issues. You can kind of game the rules in these programs, and people absolutely do it. And it's not like a small amount of money. Like these Bitcoin mining companies are making like millions per month doing stuff like this. So
Okay. You just.
you're like just gonna invest it. Some like China has banned Bitcoin mining in part for reasons like this, and other countries may as well. But in the great state of Texas, that's very unlikely ever to happen. And like a quarter of the world's Bitcoin mining now happens in Texas, basically for these
It
reasons.
has nothing to do with Bitcoin.
Oh, okay, cool. I'm getting so far off track here. I apologize. But anyway, we can finish up next lecture. So yeah, so it turns out that this is, in addition to having these kind of weird gameability issues and being sort of illogical, these load reduction programs actually are non-convex. So maybe their worst sin is that they don't fit in neatly into our optimization framework. Anyway, so to maximize the revenue from one of these demand response or load reduction programs, you basically want to minimize the negative of the revenue. So that's just delta T times our price times the max of 0 and our load reduction. So the max function is convex. So convex of affine, that's convex. And then we're taking a negative multiple of that thing. So negative convex is concave. So we're trying to minimize a concave function, which is not something that's permitted in our convex programming framework. But you may want to do this anyway, and there's an easy way to do it, which is just to ignore the fact that you don't get penalized if you overconsume, if you consume more than your baseline. So if you just ignore that and you pretend that you do get penalized for overconsuming, then we have a linear function rather than this concave function. And then that we can plug into our optimization neatly and so forth. Okay. I think we're getting to the end here. Yeah, okay, so reference tracking. So the idea here is that we have some power signal given to us by somebody, probably the grid operator, the ISO. And then our goal is to kind of wiggle around our power consumption, maybe relative to a baseline or maybe just the absolute power consumption in order to track this signal. And so we want to minimize something, basically an error, like how far we are from hitting the target. And we could do that in numerous ways. One is we could look at the mean absolute tracking error. So here we look at the absolute value of the difference between our actual power and the power we were trying to hit, the target. And then we take the average of all those absolute values over the time span. And so that ends up being just a 1 norm penalty divided by k. So the 1 norm is just the stuff here that ends up in the summation. We could also minimize the root mean square tracking error. And so here we would add up all the squares of the errors. Those again are 0 if you're right on, and then they grow quadratically if you're far away. And we take the mean of that and then take the square root. So root, mean, square. And that ends up just being the 2 norm divided by the square root of k. And then we could also look at the maximum absolute tracking error, sort of in the worst case, how far are we? So there we would just look at over the whole time span, how far in terms of absolute value were we from the target. And that ends up being identical to the Chebyshev norm. And so all of these are convex. We talked about norms being kind of a canonical example of convex functions. So all of these are convex because norms are convex. Okay, so even in the nonlinear objectives, actually most of them are very mildly nonlinear. And they're nonlinear in ways that actually through reformulations, we can get them into a linear programming framework. So most of the nonlinearities here come either from the max function, the min function, or the absolute value function. And we can reformulate those, and actually CVX, the toolbox of MATLAB or CVXPy in Python will do these reformulations for you. So you don't have to think about it, but you can just know that this is what's happening and behind the scenes. So if we were trying to minimize the maximum of two variables, that's equivalent to minimizing some new variable z subject to these constraints, that z is bigger than both x and y. Similarly with the min, we can do a similar game. And then with the absolute value, if we want to minimize that, for example, to minimize a tracking error term, something like that, that's equivalent to minimizing a new variable y, subject to the constraints that both x is less than y and negative x is less than. And we talked a little bit about that a couple of lectures ago. So, so this is really cool. It's great news for us because it means that linear programming is kind of not all we need, but most of what we need to solve a lot of interesting DER type problems. And linear programming basically is the oldest, most stable, fastest, and most robust kind of optimization that there is. So this puts us in a pretty good place computationally. But we did have one thing that can't, through these modeling gymnastics, be cast as a linear thing, and that was the 2 norm penalty that we have on tracking error. So if you use a root mean squared error criterion rather than, say, a mean absolute error criterion, then you're dealing with either a quadratic program or what's called a second order cone program. Okay, so let me go through the summary slide, and then I think I will stop and show you, there's an example at the end, and we'll go through that next lecture. Okay, so we basically talked about a whole bunch of DER objectives, and some of them are like bad things that we want to minimize, others were good things that we wanted to maximize, stuff like flexibility or load reduction. But I'm formulating them here kind of as all sort of costs, stuff that we want to minimize. So we talked about how if you want to maximize something, equivalently, you can just minimize the negative of that thing. Okay. So anything related to energy is basically cool with one minor caveat. So if we care about energy efficiency or the energy cost with time varying prices, those are both affine and non-decreasing in P, which is great. That means that we get sort of convexity in the basic decision variables, the state and the action that we're trying to wiggle around in our DER optimization. But if we have a negative price somewhere over the time horizon, so say just at 2 in the morning, there's a ton of wind, and so we get negative 0.01 cents a kilowatt hour, just a tiny negative thing. CVX will throw an error in that case. So you probably want to just, bump it up to 0, basically. And the reason for that is that we get affine, but not non-decreasing. So the monotonicity thing breaks, and that can cost us. And then with reduced net metering, we have a convex function, but it's also non-decreasing, which is cool for us. Pollution and the cost of pollution, both affine and non-decreasing. We talked about reference tracking error. These are convex functions of the electric power, but they do not have monotonicity properties. So sometimes they're increasing, sometimes they're decreasing. So we have to be a little bit careful with these. And sometimes if you want to do a tracking type problem, you may need a little bit of a reformulation of your physics or an approximation of your physics to be able to use convex optimization. but it's not too hard. And we'll talk about one of those next lecture. Peak demand, convex and non-decreasing. And it was convex non-decreasing, even if we had a target demand limit, even if we had kind of the coincident peak demand thing, all of them end up being convex non-decreasing, so we're fine. And then the stuff that we might want to maximize, so the flexibility, upward flexibility, that's affine and non-decreasing, we're fine. Downward flexibility, though, is affine and non-increasing. So that can cause problems depending on the DER that we're working with. And then symmetric flexibility, so there, if we want to maximize that, we get a convex optimization problem, but again, no monotonicity there. And then finally, we talked about load reduction, sometimes called demand response, although in my mind, demand response is a broader term that includes things other than just kind of reducing load on demand. But that sort of, as formulated in demand response programs, typically it's a concave function that we're trying to minimize. And so that basically is not valid in our framework, but we talked about an affine approximation to that function that'll work just fine for us. Okay, so let me stop there and we'll come back to this. I'm already over time. So okay, thanks all, and I'll see you on Thursday, which I realize is the day before spring break. So if you're not here, I won't be sad. I'll record the video and so forth.